Yes. So we can see. No, we can. Yeah, we can see it now.
See the presentation?
Yes, we can see the presentation. Okay, please go ahead. Can you just like speak closer to the laptop maybe because your voice is very low?
Right. So thank you so much for the introduction and the organizers to invite me and talk on the topic until boundary layer flows. Right. So lay down objectives of my studies. We'll be looking at the laminar.
Sorry to interrupt, Harvansh. Your voice is very low. Could you like maybe speak closer to your laptop?
Is it better now?
Yeah, it's a little bit better now.
Okay. Okay. Thank you. To lay down the objectives of my work, we are going to first look at the laminar instabilities in the boundary layer formed over an airfoil surface. We are going to see the non-modal growth, which is the bypass mechanism for transition from laminar flow to turbulence flow. We're also going to incorporate a LQR-based controller in the form of wall transpiration, which is basically suction and blowing in of the fluid from the boundary or from the wall of the airfoil. And we are going to see how this non-modal growth decreases if we are able to achieve that. Right. So I'm going to introduce a couple of topics about which my research revolves around. So hydrodynamic stability is defined as the stability of any other mechanical system where we disturb it from one equilibrium and we try to analyze if this disturbance is going to grow, is going to decay, or is going to stay as it is with time or with respect to space. Right. So linear stability analysis is the mathematical tool to analyze if these disturbances are going to decay or grow in time or in space, whatever you're looking at. In our work, we are looking at the evolution of disturbance with respect to time. So linear stability analysis has some assumptions that the perturbations incorporated in the base flow are very, very small, and we can safely neglect the non-linear terms, hence the name linear stability analysis. We'll be solving the incompressible Navier-Stokes equation superimposed with the perturbation. So to derive the governing equations, we add mathematically the perturbations to the base flow or the primary flow, and we write the equations in for our work we are writing in the terms of perturbation normal velocity and perturbation normal vorticity as the variables. In modal analysis, we assume an exponential time dependency of disturbance. Hence, we will be just looking at the sign of this omega, which is the eigenvalue of the entire problem. So our problem narrows down to an eigenvalue problem, and we need to look at the sign of the omega, and we'll be judging that how our disturbance is going to behave with respect to time. So this is exponential dependency, and it's true for asymptotic time. And we assume that the modes are independent of each other, and we focus on just one most unstable mode. In non-modal analysis, we focus on how these modes are interacting with each other. So for a lot of shear flows, with even though they have stable eigenvalues, it is observed that they tend to go in the transition at an early stage than the predicted critical value by the modal analysis. So as you can see in the figure, phi1, phi2 being two vectors, which are decreasing individually with respect to time. But however, their resultant f shows an algebraic short-term growth, and then eventually it also becomes zero when both the disturbances or both the vectors become zero themselves. So this is the main theory of why we are going to look at the non-modal analysis for our flow. We'll be finally incorporating the LQR-based controller. So we assume that we have the knowledge of the system, of the fluid system, and then we incorporate sensors and actuators on our flow system. And these sensors, what they do is they sense how the disturbance is going to behave, or primarily to see how the flow is going to change, or how the flow is going to change with time. It's going to be stable or unstable. And then it sends the signal back to the controller. Controller, on seeing this, determines what it needs to do in order to modify the flow in order to manipulate the flow in such a way to make it as much stable as possible. And then the controller sends the signals to the actuators, which actuates the mechanism of wall transpiration, actuates the mechanism of suction of fluid or blowing of fluid from the boundary, therefore changing the primary base flow and changing the stability of the flow. So here are some previous studies that we take use of. So the spark started when France in 1904 used suction of fluid from the cylinder wall in order to prevent the flow separation. In our work, we take use of mainly the work of Bewley and McKernan in terms of we adapt their method of calculating the non-modal growth and how we incorporate the controls, the linear control in the fluid system. So coming back to the base flow, we have an airfoil. So we chose NACA 2512 airfoil. This is just a random choice, an ad hoc basis choice. This method works very well on any other sort of airfoil. To obtain the base flow, so if you can see in the figure, we choose different locations on the upper surface of the airfoil, and then we draw tangents on each of these locations. And then we have the slope m, the distribution of the slope m for different tangents, different locations. And then we approximate this the flow as the boundary, the Fachner-Scan boundary layer equations, as it's the equation of flat plate, inclined flat plate of a flow over a wedge. So if you see somewhere in the middle, there will be a tangent which is horizontal, m corresponding to the slope equals to 0, m equals to 0. And that would be corresponding to the Blasius boundary layer equation. And towards the leading edge, we have a positive value of m, and towards the trailing edge, we have a negative value of. For those who have little knowledge of aerodynamics, we know that towards the trailing edge, there is unfavorable pressure gradient. So that is just something to keep in mind while seeing the transition mechanism or while seeing the non-modal growth at this particular region, or for all the regions that we are considering. Right, here are the obtained base velocity for different locations. So this is the base velocity capital U, and this actually should be U dash, which is the first derivative. And we are obtaining them because we need them for our stability calculation, which will be discussed in the coming slide. We also have the double derivative of the base velocity, as we also require this for the stability calculation. Coming back to the non-modal analysis, here we do not assume an exponential time dependence. We treat our disturbance as a function of time, and we want to look at how this disturbance is going to grow, going to behave with respect to time. So basically, we are solving an initial value problem here. So the disturbances are written in the form of normal velocity, normal perturbation velocity v, and normal perturbation vorticity eta. And these are the Orr-Sommerfeld equation. The primes represent the derivative of derivations. And this is the function of base velocity, Reynolds number, and wave number. Following are the boundary conditions that we are applying on our system, that at the boundary there is no penetration, no slip. So the perturbation die down at the boundary. And at the free stream condition, the perturbations are. We are discretizing our y domain as the Chebyshev's collocation point, which is given by yc. So if you can observe this discretization is best for stability calculation in boundary layers, since this is clustered towards the boundary, and this is that's exactly what we need to capture more. However, in our work, we have just one boundary and one free stream condition. So we are taking a mapping from yc to yr, where gamma is the stretching factor, how much points we want to stretch, in different directions. So this is the stretched discretization, where we have even more clustered points at the boundary, and less clustered point at the free stream condition. So non-modal growth is actually based on the mathematics that the operators that govern the perturbation behavior are non-normal in nature. But then um, how do we capture the extent of this non-normality of the operators? So there can be different measures of this normality depending on different sort of works, different sort of what you want to look at. So on some of the work that I have read have taken shear stress or skin friction as the measure of this of the growth. And here we are taking the energy, the perturbation energy. It is done for the ease of calculation, but if we were to look at the skin friction, we could also. So we defined something called amplification factor GT, which is the ratio of perturbation energy at time t to the perturbation energy at initial time. So XF actually represents the state of the perturbation at time t, and this energy is dependent on the state. So energy is a function of time because state is a function of time. Right. And so this growth curve has a peak which we call Gmax, and we'll be seeing it in. So now we are going to incorporate the control. So as I discussed before in the control side, how the controller and actuators and sensors are incorporated in a real system. So mathematically, we are going to add this control in the form of perturbation velocity, and specifically in the form of the normal velocity. So we could also look at the tangential velocity, but here, just for the sake of easiness, we are looking at the addition of control in the form of velocity, perturbation velocity. So the normal perturbation velocity v tilde now has an addition sum Fy and Qt, which is the control sum, and the eta, which is the normal vorticity, it remains as before. And when we put these terms back into the equation, we obtain a complex form which we call state space model. And here x is the vector, the perturbation velocity vector, and the dot represents the time derivative of the perturbation vector. And q is the control input, which we still don't know. So to obtain q, we form an optimization problem because we want to optimize our system in terms of reducing the energy, reducing the perturbation energy. So we form a cost function j that has energy and the control input. It's integrated over the energy is integrated over the entire domain. We find out what is the appropriate output or the appropriate feedback Q, which is to be given to the system in order to manipulate the system so as to get minimized energy. So we take use of LQR controller as this is best suited for multiple input, multiple output system, which our system is. And since it's also follows linear term, so this is best suited for our kind of system. So we obtain Q in the form of the state vector x, and finally we arrive at another initial value problem, which is optimized because of the LQR integration of LQR controller. So we validated our results using the previous study where we mapped the parameters to Reynolds number and wave numbers according to their study, and they show good agreement. So this is how the growth curve GT looks like. So even though this flow is stable, there is initial growth of energy, and then finally the growth becomes zero. Finally, the perturbation decay down. But this growth is the most critical one because this can trigger the entire flow, and the entire flow can go into an early transition, which was the bypass mechanism. So we calculated the contour for the peak point Gmax for the Reynolds number 160 and for different locations. So M is the slope at the different locations. So M represents the different location on the airfoil. And it is no wonder that the maximum of the maximum, the supremum Gmax is obtained at alpha equals to 0. And the beta was corresponding to 0.3 or 0.25. So now we are going to pick the most critical pair of wave numbers, which is alpha equals to be 0 and beta to be somewhere 0.3 or 0.25. And we're going to see the growth and the effect of control methods, particularly for those pairs. So this is for Reynolds number 160, alpha equals to 0, beta equals to 0.3, and for 3 different locations airfoil. The blue curve in each of the graph represents the energy amplification without control, and the red curves represent the energy amplification with control. So as you can see that there is a significant reduction in all the graphs at all locations. But you can see that the reduction in this growth is different for different locations. So that happens because of the controllability of the matrix. So we have not looked at the mathematics of how the controllability is affecting this control. Yet this is just from the literature that I have read, that this controllability of the matrix comes into picture when it comes to why certain reduction is happening or why certain reduction of certain parameters. So now if you just consider the first figure, and this is for Reynolds number 160. If you increase the Reynolds number with control, you're going to get a curve slightly higher than this. If you increase further, slightly more higher than this. And if you keep on increasing the Reynolds number, you will reach up to a particular Reynolds number where with controls, you will get the same amount of Gmax as you were getting for Reynolds number without control. So that shows how much increase in Reynolds number that is possible with control, so as to achieve the same flow scenario in terms of the growth of perturbation. So this is how we increase the Reynolds number bit by bit with controls, and we see up to what Reynolds number with controls matches the same growth as a lower Reynolds number without control. So for different locations, again, it's going to be different. So for m equals to minus 0.05, which is towards the trailing edge, we could reach up to Reynolds number 2.5 from 160. Yet the flow remains in the same stable scenario. Right, and for m equals to 0, we could reach up to 1.5. For m equals to 0.05, we could reach up to 0. So this is the overall scenario.
Sorry to interrupt, Harvansh. Maybe could you complete in a couple of minutes, please?
So this is how the Gmax at different locations looks like without control and with control, and we can see that the reduction in the control is different because of the controllability, and this is the percent reduction in Gmax at different values of m. So a maximum of 60% we could see is achieved using our method. To summarize, we saw the base flow for the airfoil boundary layer by approximating the base flow using the Fatner scan boundary layer flows. We looked at the non-modular growth, and we incorporated the LQR-based controller, achieving a maximum of 60% reduction. So that's all for the talk today, and thank you so much for your attention. I would be happy to take any questions.
Thank you very much, Harvansh, for your presentation. So any questions from the audience, please go ahead. Maybe I can ask a quick question. So you talked about stability analysis. Now, would you be, I mean, you didn't talk about this, but would you be able to say anything about comparing your method with something like triple deck theory? With
I don't really know about that.
Okay, no, that's okay. So it's just something that is able to like predict separation and things like that, boundary layer separation and stuff like that, where they instead of having one, you have like three boundary layers where different things are happening in each of them. So I was just wondering if you can make any comment about it. That's okay, no problem.
There's a talk about that, but I'm not very well versed with any.
I understand. No worries, no problem. Any other quick question maybe from the audience?
I think there is a question in the chat, if you can see.
Okay.
Um,
Okay, so there's a question from, I can read it out. Sarfraz Hussain asks, hi, do you have a comparison with any experimental work?
No, we have not done any comparison. The validation was made.
Okay, thank you. So in the interest of time, maybe we can wrap up. And if there are any further questions, of course, you can email our speaker. Okay, so thank you again, Harvansh. And let us now move to our next speaker, who is Professor Arusha from IIT Madras.